You're seeing the screen, eh?
Yeah, I'm seeing it. You can
Let me first
proceed.
start by this thanking our presenter, Mr. Gilbert, who has given us brief but this detailed and understandable explanation of classification. And I believe by now, at least, if we put our hands on classification, the next time we might not be confused, and at least we should be able to know the details or the output of program, though we might not be familiar with the codes, but we shall at least know what the output is. And for me, I'm not going to have much of a talk because a lot has been spoken by our first presenter. So we are just going to dive into our hands-on session direct. We are going to train a model, a hotel reservation model, like a model which can predict basing on given input variables whether a hotel booking. Okay, are we all on track? Hello?
Yes, I'm hearing you.
Like I said, we are going to build a model which, basing on a given input variables, and be able to detect whether a booked day reservation is actually going to be cancelled or not. So let's delve into it. And the first thing, I'm going to use Jupyter Notebook, though you're welcome to be using any of the editors you're familiar with, being it Colab, being it Kagos Notebook, be it Visual Code. You're welcome to use it, but for now, I'm going to use Jupyter Notebook, and that's what I'm familiar with. Uh, I'm going to create a new notebook. Maybe let me just call it hotel reservation. We're not going to spend much of time here, and I'm going to make this a detailed step-by-step build up. By detailed step-by-step build up, I mean we are going to do one step at a time. We finish at it one step, even if there are errors, we debug it, then we move to the next step until we finish the build up of our model. I promise you by the end of this session, at least we shall be having, if not we go back with 6% of what is being taught here, we shall be having the zeal of going to learn more about what has been said here. That being said, the first step we are going to do is to import all our libraries, the libraries we are going to use. First things first, as you know, the first thing to import is Pandas library for doing data manipulation. Yes, let's import Pandas, and we're giving it an alias of PD. And let me hope you are all familiar with what the alias PD does by now. Let's import our Matplotlib library, matplotlib.pyplot, plt. Let's import another library called the Seaborn, and we're importing it as SN. And this is for data visualization. We are just going to do some brief data visualization on our dataset. And I forgot to tell you, the dataset we are using here is an open source set from Cargo, which is a hotel reservation dataset. You just go to Cargo and you search for hotel reservation and you get the dataset. And that's the dataset we are using. After importing Seaborn, we are going to import from scikit-learn, from sklearn.metrics. from SQL and metrics, I want my accuracy score.
Ahmed, it's like we are not hearing you. Ahmed, are you hearing us? Ahmed, you hearing us? Ahmed, Ahmed. No.
Are you getting me?
I think we can hear you.
Are you hearing him?
Gilbert,
Yes?
are you getting me now?
Yeah, we are getting you.
We are still at the level of importing all our libraries, the libraries we are going to use. We had 3 of them already. We are going to import again from sklearn dot module selection. Module selection, we are going to import a library, a function called print test split. Print test split. Small typo error here. We have another library from sklearn dot preprocessing. We are going to import our function called one hot encoder and one called label encoder and another one called the standard scaler. Let's import the algorithms we are going to use. Mr. Gilbert talked to the KNN library, the KNN algorithm, I mean, and the decision forest and the random forest, all those. But truth be told, no algorithm by the look of things can be said that it is better than the other unless you try to experiment it, see which algorithm does good for your own case. You get? So we are going to try, like, for the sake of time, we shall be trying, let me say, two algorithms, and we see which of them does best for our own case. And we shall not just conclude by things that say KNN does better than a decision forest, or the decision forest is better than the logistic. No, we are going to use two of the algorithms that we see. The first algorithm we're going to use here, I think, is the logistic regression, which we say from sklearn dot linear model. We are going to import logistic regression. Now again, we have from sklearn dot. We are going to use, let's use the KNN, and we also see from sklearn dot neighbors. We are going to import our K neighbor classifier. I think from here we are done with our first step. We said we are going to do a step-by-step build up of our model, meaning we finish one step and we proceed to the next. So we have finished the first step, which is the step of importing our
Ahmed,
library. Yes.
Ahmed,
Yes. I get.
like sometimes you speak and then your voice goes down.
Maybe it's network. Network is not kind of stable. Sorry for that. I get now. Hello.
Yeah, I think you're audible.
Okay. Yeah, I was like, we are done with our first step, and our first step was importing all our libraries. So the second step is reading our dataset. We now want to read our dataset and we see how it looks like. Yes, I'm calling it DF, though you can call it anything of your choice. For convenience sake, I'm just calling it DF. Let me say DF, and we're doing PD to read CSV. And I have my dataset T already, which is inside of my hotel reservation.csv file. So reading it, let's now have a visual understanding of our dataset by doing DF. Now this is how our dataset looks like, with, I think, around 19 rows and 19 columns, and around 36 plus rows. So, with machine learning, anything to do with machine learning, we talk of data, we talk of data sets, and the most important thing is doing your data analysis. And if you dare ask any machine learning engineer or a researcher or a practitioner, he or she will at least tell you that the most time consuming part of machine learning is dealing with EDA, doing data analysis. So we are going to spend we're going to spend a bit of time here to do our data analysis and our data set, how our data set looks like, how it works, the relationship between the inputs and the output variable, all those things. We do the mixing values. We see how we can change our categorical values into numericals, all those things, right? Am I audible?
Yeah, you're audible.
Okay, thank you. Yeah. Now I was saying we are at the step of doing our EDA now. So we have our data set, we have our data, we have the visual representation of our data here. So we see how we are going to understand our data set. We find the missing values. We see how we see the input, the relationship between the input variables and the output, all those things, right? So the first thing we are going to do here is a little bit of data visualization. We're not going to do much detail of it, since data visualization is also something of its own. It's also something of its own, which has to be given time. So we are going to just do a brief data visualization aspect here, and we understand one or two of our input variables. So the first thing we are going to do is, if you remember, we imported a library here called Seaborn, and this is a library for doing advanced data visualization. That's the library we're going to use. We're going. Let me. We have SN.
Ahmed, I don't know whether I'm the only person who is not hearing you or
Even this is the same issue. Am I the only one who's not hearing?
Ahmed. Ahmed. Let me try.
I come.
Hello, are you getting me? Aloysius, Andrew, Tracy, are you getting me?
You're getting me. You can continue. You are getting me.
Are you getting already? Right, was some simple network problem. Apologies for that.
We are getting you.
Yeah, now I was like, we are doing another visualization for a histogram to see the number of days which are mostly booked, like the frequent number of days which are actually used, so that you can also try to draw some conclusion from here. Now you're putting yourself, now you're looking at this in the perspective of being a data analyst, and you're analyzing it. You want to draw a report and give it to the manager, something like that. And you see, like, you say from Monday to at least Friday, these weekdays, they're kind of busy. And you try to draw conclusion from there. You can now say, since from Monday to Friday, the hotel is kind of busy, I can say it is being used by travelers. Mostly the books come from travelers. And for the weekend, you see the number of books are not all that many. You can just conclude and you say the hotel from Saturday to Sunday is mostly used by the people around, because yeah. Now we want to draw a histogram for it, and we just check the number of weeknights. Let me paste it here. And I have a color. Let me just put a color for it. Takes another parameter called color. Let me just call it red, though you can also put anything of your choice there. Then I I have my label. Let me say my label is, let me just call it weeknights, weekday nights. Let me just copy this, and from here I change this to from weeknights to, let me say weekend, number of weekend nights. Here, and I change the label to maybe, let me just call it weekend nights, and the color should be blue. Then I do plt dot title also. I can say weekend nights versus weekday nights. Then I do plt dot, let me say X label, and I say, let me just say this is weekend nights and weekday nights. Then I do plt dot show. Yeah, we have two of our visualizations here. One is the count plot for the type mill, and the other one is a histogram for our weekend nights and our weekday nights. Now from here we can at least do some conclusion. Maybe I add something here a little bit. Let me just put a legend, plt.legend, and you see plt dot.
The link has not yet.
Yeah, here we can see the bars with the red color are the number of weekday nights, and the bars with the blue color are the number of weekend nights. Now at least from here we can sit down, analyze it, and draw a conclusion from here. We say our hotel is mostly used during weekday nights, and you can say maybe there are travelers who are mostly using our hotel now. You get, so data visualization as a whole is a very powerful tool in data science. In the context of machine learning and data science at large, it is a very powerful tool. At least it is a must-know tool. So maybe we shall organize a session for it, a session of its own. We talk more about only data visualization because it's a very powerful tool. And with it, with data visualization alone, you can stand out because it is a time-consuming thing. So people mostly tend to not learn it; they tend to ignore it. But if you have it, at least you can be a standalone, whether a ML practitioner or an engineer or a researcher. Yeah, this is all for our data, all about our data visualization. Now let's analyze our data again, our data set again, and we see which of these columns are not all that important. Like they don't give much impact to our output variable. From here, our output variable is the, I think our output variable is booking orders from here. So we can see which of these columns do not have much impact on our output variable. get are you get are you get are you hearing? Yeah, yeah. Okay, okay. Yeah, I was saying we do not have much
Guys, you're not hearing me. Administrator, can you confirm if you're hearing me? Yes? Uh, Chris, are you hearing me?
Yeah.
Okay, maybe it's let me confirm with Ahmed and see.
are you getting hello? Guys, are you getting me? Are you all getting me? Are you all getting me?
From I can
Are you,
hear you.
you hear me?
Yeah.
So we have to separate our output variables from the inputs. Let me just call it X by convention. So you can just call it anything of your choice. And I'm going to do df. I'm going to use a function in SQL called pylog, which works hand in hand with Python's slicing. If you've ever worked in Python slicing, you be familiar. So we have another way of doing it. So I'm going to I want to get all the rows, but of the first column up to the second. Yeah, I think we are good to go with the X. And for the Y, I'm just going to say Y equals to df.ilog, df.ilog, but this time I need all the rows, but this time only of the last row, right? So from here, if I do X, you can see I have these rows without the output variable now. Meanwhile, if I do Y, I'm only getting the output variable. Right? Now from here we are going to do, if you see our data set, we have strings in our data set, and ideally machine learning algorithms work with numerics. So we have to converting these strings, at least their numerical equivalencies, right? So that's your thing like one hot encoding or label encoding. That's where they now come into play their roles, right? To maybe convert the output by the numerical the strings I mean into numerics now, right? So we are going to do another coding, but we have to import another library. Let me say from SQL dot compute. We have to import the column transformer, right? So let me create an instance called the city for it. And the city will have the library of column transformer, which takes another parameter called the transformers, and the transformer will now that's now where we do the label encoding thing now in action. We give a name for it, any name of your choice. I can call it one hot. Let me call it one hot one. And what I want to do to it is one hot encoder. Now what I want to do the one hot encoder on which column? You check the column in a string. I think this is one of what you want to do. Let me just copy it. I paste it here. So we do another one. Call it one hot. Call it one hot two. It is we do one hot encoding to it. And which column? Let's see which of our column needs one hot encoding. let's see which of our column needs one hot encoding. I think this one here needs one hot encoding. I copy and I paste it here. Let me do one more because I think the three columns there need one hot encoding. The other one is market segment type. I copy it and I do. Let me give it another name of one hot 3. We are doing one hot encoding to it. On this column. From here, I'm going to just simply do remainder. Remainder is the first row. It means after doing one hot encoding on these columns, you leave the other columns the way they are. Right?
I'm not hearing.
Members, if you don't hear, you should confirm with us because network is not so good. Don't keep quiet if you're not hearing. So are you hearing him?
No.
Wait, Ahmed. Ahmed. Ahmed, I can't hear you. I don't know whether I'm the only person who cannot hear you.
You getting me? Yeah. Let me hope everyone is getting me now.
Yeah.
Yeah, we were here completing our node encoding, and I think from here let's try running and we see. We're gonna have a closing parenthesis somewhere.
Ahmed.
I think we're fixing some bug here. Coding is all about fixing and trying things out. So we do remainder equals to pass through. Yes. Now if you do, now we're going to do CT. We create an instance again X, so you can create anything of your choice. Now you're going to do this column, you are going to do column transformer on the X variable that we created before. So we do CT dot transform fit transform X. And if you run X, you can see this is what we have, but it is giving us an array, so which is not human readable. So we have to transform it into something which is kind of human readable. So I can say X is, then I create a data frame for it. The data frame, and the data frame will include X, which is this array, and the columns will be this the one hot encoding we have done. So we do ct dot get feature frames out, and when we run this, now when we do X, this is what we now have, but this is something which is kind of human readable, but with the one hot with features being one hot encoded. So from here, I think we are good to go, but we also need to do a label encoding on our output variables. So we are going to do a label encoding now. So let me create an instance for it. Let me just call it label, which takes the function label encoder, and I do my y equals to label dot the label encoder label dot fit transform now, and I'm fit transforming the y now. So when I visualize y, I can say I have an array of zeros and ones now. At least this is what we actually expect to get. So from here, I think we are good to go. We are now remaining with splitting our data into training and testing to see how much of our data will be given to training and how much of our data will be given for testing. So we are going to do X train and X test. We have Y train and maybe Y test, which we'll put it into the library, the function we imported, which is the train test split. It will take in X and Y, and we also have a test size for it, which is 0.2. Maybe you can do a random state of 42 for it. And if you run, we have it. When you do X train, this is what you have. Part of our data set is being given for training. You can see around 29,000 of our data set have been given for training. And if you remember, we had almost 36 plus of our data set for training. 36 data set as in general, but 29 will now be allocated for training, and the rest will be given for testing. So from here, I think that the next thing we are going to do is at least do a standard scaler. If you can see from here, our data is of various ranges. There are some of around 25, 14, and there are some 1. It means the range is not, the data it is not in range. So what we want is to bring our data set in one range. We want to give it a range of values, maybe starting from -1 to 1, something like that. So we are just going to do scalar. We create an instance for the standard scalar because it is the standard scalar that we are actually going to use. It is the standard scalar function that we are going to use to give our data set a range of values. You get? So we are creating an instance for it. Maybe we say standard scalar. Then I'm doing this. Doing the standard scalar on my X train and my X test, right? Because it is the X train and the X test that is containing our input variables. So we want to do the training, we want to do the scaling on them. So I'm going to say my X train equals to scalar dot fit transform X train, and we also do the same for X test. Let me just copy this for the sake of time. We do it on X test. I call it, I create a variable for it called X test. Now when we try visualizing X train, you see we now have at least a range of values, which is, I can see it is ranging from negative to at least positive, from negative something to positive something. It means we no longer have our 24,000s, our 14,000s. We now have a range of values, right? Now this from here, at this point, we can confidently say we are done with doing our EDF for this data set. So we are now going to proceed into training our model now. Okay. So we had imported around 2 algorithms to use. So we are going to use the logistic regression and the KNN. The first algorithm we're going to use is the KNN. Let me do a model. Let me create an instance for it called model, and it is a k neighbor classifier which has n neighbors. We say 3, and maybe the matrix. The matrix is actually the distance you want to use to because you know KNN works with distance. So which distance do you want to use for calculating? Okay, so they are also there. So what are with the distance I'm going to use here is, let me say the Manhattan. The Manhattan, though there are some you can use the Minkowski, the Manhattan is there. There are more that you can use. But for now, I'm going to use the Manhattan. Yeah. Then I do my model, the fit. What am I fitting? I'm fitting the X train. I think my Y train, right? The our model is good to go. Now let's predict. Let's predict our model. We now predict it. Let me call it. Let me create an instance or a variable for it called Y predict. Then I'm going to do model.predict. Model.predict. What am I predicting? I'm now predicting the X test because the X test is the data which it has not seen. So I want to see how it is going to perform with the data which it has not seen, which is the X test. And let me just also create an instance for the accuracy for me to see the evaluation of it, how best it has performed. And I create an instance for the accuracy score, and I'm doing the accuracy score on my Y predict. On my Y predict and my Y test now. Because I have my actual Y test. Y test is my actual predictions, right? Then the Y predict is what it is a variable which contains the predictions. Now I'm going to check how best my model has performed based on the actual output, right? It means Y predict is a variable which contains my predicted outputs. So I'm going to check how best it has performed. So let me just print it out in an F string. And I call it accuracy. Then I pass to it the instance I've created called accuracy. But this time I want to do it into two decimal places, I think. Yeah. Running it. Wait for it to train to predict, and we see it means our model has an accuracy of 85%. If you can see, our model has an accuracy of 85%. So let's do a confusion matrix for it, and we display it, and we see how best it has at least performed. We can analyze it better using the confusion matrix, or you can also go and research more about things like the classification report to give you more insight on seeing how your model has performed based on the given data, right? You now see whether is it the problem of the algorithm or it is the data set's problem by doing the classification report. That one I will leave it for you. You go and do more research about it. It means for now we are just going to do a confusion matrix for it, right? Let me create an instance called CM for the confusion matrix. We have the confusion matrix, and we're doing the confusion matrix on Y predict. Remember, we said Y predict is a variable which contains all our predicted outputs, and Y test is the variable which contains our actual outputs. And then I'm going to create another instance called the display. Let me call it display. Now I want to make a visualization for the confusion matrix. You remember we imported a library, a function here called the confusion matrix display. And this is what we use to give us like a tabular format of our confusion matrix, right? So let me just say I call my confusion matrix display, and it takes a parameter called confusion matrix, but we have an instance for it called the CM. And it has takes another parameter called the display label, which takes on the model dot classes, right? Now we let me say display dot plot. We do a display dot plot with a CMAP And this CMAP parameter is actually giving us a color of our confusion matrix, right? Let me call it blues, and I do plt.title. plt.title. I give it a title of my choice. Let me just call it confusion matrix display. Then I do plt.show. Now we have the confusion matrix display here. Let me remove maybe the axis. plt.axis, which is off. So we have our confusion matrix here now. You can see, let me say we have 1 as our true positive and 0 here as our true negative. Or let me say 1 is positive and 0 is negative. So now see the predicted label is saying 0 and 1. Now for this value of 1, which we have positive, and it has predicted 0, which is negative, we say this is a false negative, right? Meaning for the prediction which is supposed to be positive and it has predicted negative, we say that is a false negative, right? And for a prediction which is supposed to be a negative or a 0 and it has predicted 0, that is our true negative, right? And for a prediction which is supposed to be a positive or a 1 and it has predicted 1, that is a true positive. And for a prediction which is supposed to be a 0 and it has predicted 1, that is a false positive. So from this table, we can see that we have around 606 false negatives, and we have 1,810 true negatives, and we have around 4,379 true positives and 460 false positives, right? This is the confusion matrix for this. And this was our KNN algorithm. So let's also use our logistic regression and we see how it is going to perform on our data set. Let me maybe comment this out, and for the moment I use the logistic. Let me say model. I create an instance for it, which is the logistic regression, and I train it. Let me predict it. It has an accuracy of 80. If you remember, the KNN had an accuracy of 85. So this one here has dropped to 80. It means for the moment, we can conclude that at least for our own case, KNN has performed kind of better than the logistic regression for our own case. But it is not a guarantee that by all means, all the times, KNN will be performing better than logistic regression. At one time, you will find logistic regression is having an accuracy of 100% over KNN. You get? So it is not a guarantee. But for our own case, we can conclude that we say that at least KNN has done better than logistic regression, and we go by that. And you have the confusion matrix for it. It has around 15,000 false true negatives, around 900 false negatives, around 500 false positives, and 4,000 true positives. So this is basically all what we had for our model. Giving it a recap, we imported all the models, all the libraries we're going to use, from the algorithms to the libraries for doing manipulations, to importing our data set, to reading our data set, or reading our data set, going ahead to visualizing our data set, to visualizing our data to see the relationship between the inputs and the outputs, relationship between the inputs and themselves, something like that. We also did a dropout of the columns that we see are not of much impact to our data. You get it means like the columns which do not give much meaning or much impact to our output variables. We looked at them and we say that maybe the booking ID and the arrival time don't give much impact to our output variables. So we had to drop them out. And from here we did a separation of our input variables from our output variables. And we use the ilog function, which works hand in hand with Python slices. If my Python developers here, if they know what I'm talking about, if you have ever worked with the Python slices, this is not, at least not something new to you by now. Because from here, we are just saying, we are using the ilog function, which will go into our data set and check the columns and the rows, right? So we are saying, this first column we are seeing here, this colon sign we are seeing here is saying, give me all the rows. You go into my data set and output all the rows there. Now, this one here is saying, after giving me all the rows, now I want to filter the rows of which column? The rows from the first column up to my second last column. And if you can see from our data set here, we have the first row, which is the number of adults, this number of adults, and it will go way up to our last column, which is at least number of special guests. It is getting all the rows, but from the first column up to our second last column. That's why we are saying we are talking of a -1 here. Okay. Now this other function, the second one is telling us, is telling the ilog function to go into the data set and get back all the rows, but only of the last column. That's why we're doing a -1 here. Though you can also, the other way of doing this is just by, you do X and you get df and you just specify all the columns you need. Maybe you just, let me say you just get all these columns from here up to here. You just copy them and maybe paste them here, but separating them with quotes now, like this. You do this for all of them one by one, separating all of them with quotes. Maybe something like this. Something like this. You do this for all of the data you've placed here. This will also give you the same output as the ilog function. But me, I'm just saying it, this one here as tedious. It is time consuming. You know, when you're dealing with computing, you're fighting time and also resources. So for the sake of time, that's why I just decided you use the ilog function. And for this y, you will have just done something like y equals to, you get the df of only something like the booking, I think. Something like booking. Like this booking status. You just get, since y is our output variable, so you just put df for the column name of the output variable. It will still give you the same output as this ilog function we have done here. Yeah, that was a recap of it. And we proceeded into doing a one-hot encoding. We said one-hot encoding is just the idea of changing our the data set, the data which had columns of the string data type to, we are changing them into a numerical data type, since machine learning algorithms work with numericals. So we have to change the string data types you have there into at least their numerical equivalences. That's why this idea of one-hot encoding comes in. But ideally, we would have done a label encoding here. But if you can see, if you do label encoding into this, what label encoding does is giving a binary equivalence of one. No, label encoding gives a numerical equivalence of 1 up to where then up to the number of separate data you're having. Let me say, for example, you have colors from green, red, blue. So label encoding will change the data, the color from give it, and it will give red equivalence of 0, gives 1 an equivalence of gives blue an equivalence of 1, and gives maybe green an equivalence of 2. So we shall be having 1, 2, 3 in 0, 1, and 2 instead of red, blue, and green, right? But when we talk of computing, we see things working in binary, right? We need either a 0 or a 1. You get? So that's why one-hot encoding steps in, because it gives you a binary numerical equivalence. Suppose we had our same column there of, let me say, red, blue, and green. Instead of converting them into 0, 1, and 2, it will check the data set. Where it is red, it will give it 1 and the rest will be 0. Where it is blue, it will give it 1 and the rest will be 0. Where it is green, it will give it 1 and the rest will be 0. So it means you can see from here there is also a lot to talk about things like one-hot encoding and label encoding. You get? That's why here we did one-hot encoding, because if you can see from here, our type of meal had a lot of differentiations in it. We had meal 1 type, we had meal 1, we had not selected. I think if you do the analysis of the data, you will also get things like meal type 2, meal type 3, which means if we are to do one-hot encoding, a label encoding, I mean, we are going to have things like, we are going to have the numerical equivalence from 0 at least up to 4. You get? But that's not what we actually want. We want things from 0 to 1. So it will just take where there is meal type 1, it will give it 1 and the rest will be 0, which means ideally what is going to happen here is that it is going to create more columns into this data set. If you take from here, we have 16 columns in our data set here, but after doing one-hot encoding, you will get that we have more columns, which means we have around 29 columns now. You get? So the one-hot encoding, what it does, it adds more columns into a data set. Where there's meal type 1, you see it is already 0. Then meal type 2 is 1. Where there's meal type 1, it is 1. Then there's meal type 2, it gives it 0. Meal type 3 gives it 0, and not selected gives it 0. And where there's meal type 2, if the column has a meal type 2, it will give it 1, then the rest will also be 0. You can see also here it is 1, then the rest of it up to here are zeros. Again, from here, there's 1, the rest of it are zeros. So this is what actually happens with one-hot encoding. So for label encoding, it is just a simple thing. You do it, changes it to 0, 1, up to 2. But for our own sake, why we did label encoding here? Because we only have 2 unique values. We had not cancelled and cancelled. It will actually give us the binary equivalence, which is 0 and 1. That's why we did the label encoding here. Yeah, up to here, and then from here we just split our data set, giving, like, allocating part of it for training, part of it for testing. Okay. And this we have a test size which is 0.2, which is actually telling our model to give 20% for testing. And we have a random state here. And this random state is actually, you know what is going to happen here is when you're going to run this model again and again, it will be given in 2 batches. You get? It will be given to the model in 2 batches for training. So like at each time, if we don't specify this random state we are seeing here, we shall not be giving it the same size. You get? Like for our case, we have around 36 of our data set. We have 36 columns. So if you're going to do We are not going to do a random state here, which means each time the model runs again, there will be variations. If let me say at this time you're giving 80, you're saying 80, but from the 80 you want these columns for training, but you have not specified the randomness, you are going to see a variation in it. You will not see it, but that is what is happening underneath the hood. You will see a variation. The random state, now this random state steps in, giving you that at each time you run the module again, the batch will just give it the same size. You get, like now when you go to things like deep learning, you see how these batches now work into action. Now if you run this model, you say at this time if I run this model, I want to give it a batch of around 32. You get, so that's why this random state now handles that thing. The next time you run again, it will just give it the same batch of 32, but with different kind of data, right? Just picking it from random, but with the same batch of 32. Now this 42 it is not a must that you should do things like 42. This 42 is okay, it is not something very important. It's just like a programming fun. If you ever read a novel, there's something like the Hakichi, a novel called the Hakichi, where you find people. There are people who are actually the group of people built a computer to answer a question. What is something like the great? I'm kind of forgetting it, but it is a novel. You can go and read it. It's called Hakichi. The people, like a group of people, join hands together to build a powerful computer to answer a question. What is the great purpose of life? Something like that. Answer the question. So the answer they got there was 42. So from then, programmers were just like using this 42 as they call it a programming fun. Yeah. So it is not a must that even if you put 42, it just has to put it. You can put anything, you can put 7, you can put 11. So this 42 is just a programming fun. They call it programming fun from the Hakichi's novel. You can go and read more about it. Yes, that is it. Then we did standard scalar is giving a range to our data set. And we saw it in action here. This is our output. Then we trained our model. We first used the KNN, which gave us an algorithm of around 85. Then we had logistic, which gave us an accuracy of 80. We did the confusion matrix. We displayed it, and we saw things like the true positives, false positives, and true negatives, false negatives, and all that. I think from here we are coming to the end of our session for now, our hands-on session. Let me hope at least everything is well explained. If there are any other questions, you pass them through before I rest my case and give the floor to the host. Let me see if there are any other questions, you pass them through before I leave the floor. Let me believe silence means there are no questions. From here, let me just thank you for listening, though there were a lot of network errors, some of the things were not well taken, but I
Okay, bye bye.